In this video we're going to do some signal processing with recordings of musical instruments. So you can see in this folder here we've got a bunch of these recordings. Let's just try one. So here's a gong, and we can just play it within VS Code. Here we've got an oboe. Okay, so the first thing we're going to do is going to just work out how to play these sounds purely within Python. So there's various different packages that you can use to do this, but the one we're going to do is called Simple Audio. Okay, so so we need this function Simple Audio wave object from wave file, and then what we do, let's do the guitar. Okay, so then okay, so this will give us an object here. Let's just see what it is. So this gives us an object of some complicated type, but it has this. Well, we could do dir wo to see what methods this object supports, and you can see there's a whole bunch of stuff. But down here it's got play, which is obviously sounds plausible. So let's try wo.play. That was a bit quiet, but yeah, so let's maybe do a different one. See if we get one that's louder. We'll go. Okay, so so there's a way to play things. So let's actually just put this into a function. Okay, so okay, so there's a function, and then we can try it. Let's say okay, so that's how we can play the sample, but we actually want to do some signal processing on it. So we want to actually get data about the sound levels at different times, and then do some Fourier transforms on it or other kinds of stuff. So for that, it's best to import different packages. We're going to we'll import NumPy as usual, but we'll also import SciPy. SciPy's got a bunch of stuff for signal processing. Okay. Okay, we're going to use the first thing we're going to use is scipy.io.wavefile.read, and then you can do okay, so we can do that. That will read a thing for us, and let's see what we've got. Okay, it seems to be a tuple. It's got a couple of stuff in round brackets. And so we've got a number first, and then an array. Okay, okay. So what's the first number? The first number is actually the sampling frequency. So we've got 44,000 measurements of the sound power every second, which will give us allow us to sort of detect frequencies up to 44 kilohertz, maybe something like that. So that's the rate. And then the rest is this array, which we'll call data. Okay, so instead of just taking it as a single object, we're going to do it like that, and then Okay, so this data seems to be 0 as far as we can see. So let's plot it. Okay, we need to import PLT as usual, and let's do it should be plt.plot. Okay, so we can see, so it is. Looks like it's 0 at the beginning and the end. There's a bit of silence, but then we've got a bunch of data in the middle. Okay, we've got about. So it's about, as I said, about 44,000 samples per second. We've got about 80,000 samples altogether, so it's about 2 seconds worth of recording. Okay, so let's maybe look at some bit in the middle then. So now we look at this. We've got it turns out all this data is actually integers, which is kind of that's kind of okay. Well, it's and we do data.dtype. It's int16. So that's how things are stored in the WAV file. But for the various kind of signal processing things, we really want to have floating point numbers instead of integers. So we'll just change the data type there. I'll convert it to float, and then the sort of range of the integers is up to 2 to the power 15. So we're going to divide by 2 to the power 15 to get numbers kind of in the range 0 to 1. So there we go. We've got numbers in the range 0 to 1 now. Okay, but now, as I said, we've got silence at the beginning and the end, and that's kind of not really what we want. So we want to work out how to extract a section in the middle of the data where we've actually got sound. So we do absolute value, because it starts with 0. Well, let's work out actually firstly what's the sort of maximum absolute value we've got. So the maximum absolute value quite small, not just 0.08. But so we're going to look at for part of the signal where we've got at least 0.04. If we look at sections where we've got the absolute value more than 0.04, then that's going to be indicate that we're sort of in the proper part of the recording. So we're going to do so we can do this kind of notation here. Remember, this is giving us this just gives us an array. Where so it gives us an array of true and false values, and it starts off false because it's silent at the beginning and ends up false because it's silent in the middle, but then there's going to be some stuff in the middle where it's going to be true. So we do np.argmax. That'll tell us the first place where we get a true, so that's in 4658. We also want to know kind of when's the last place. So we can do. So one way you can do that, we can do. So we do remember data : -1. That's the standard way to reverse your data. Okay, so now we're finding out where we've got data that's sort of looking from the end for stuff where the absolute value is at least m over 4. And then we do mb.argmax that. Okay, so that's how many spaces we have to go from the end to get power of at least m over 4. But then we need to sort of, that's counting backwards from the end, so we need to sort of subtract from the length of the data, like so. Okay, so that's kind of going to be the end. So let's call this A, which is going to be where we start our data, and then we'll call this one B, and then okay, so so now we've cut down our data, so we should have no silence there. Okay, so we can so now, you see we've cut it down, so so we've got real signal there. Okay. Okay, so now now we want to take a Fourier transform that'll kind of tell us what frequencies are involved in this signal. Yes, we could do there's the Fourier transform and the power spectrum are both kind of slightly different ways to approach that question. In this video, we're going to use the Fourier transform. Okay, so so there's kind of it's actually a basic Fourier transform package, discrete Fourier transform package. It's built into NumPy, but there's a kind of more elaborate one that's built into SciPy. We're actually not going to do anything very elaborate here, so we could have used the NumPy version, but mostly we're going to be using SciPy stuff. So for consistency, we're going to use the SciPy version of the fast Fourier transform. So so this will tell us kind of how much signal there is at different frequencies. So we're going to take that. Okay, so you can see this is giving us an array here, and you can see that there's this bunch of j's here. Remember, j is your Python notation for the square root of -1. This is ft is an array of complex numbers. So let's plot it. So we can plot the real parts. Notice there, this is kind of a symmetric thing. It's the same looking from the right, if we read it from the right to the left, and then actually we can plot on the same. Okay, so yes, actually it's not so easy to see what's going on here. Let's just do a kind of smaller part. Okay, so this is what we get for the first kind of initial segment of the Fourier transform. But now let's look at the end of it. Look at the last 100 points in the Fourier transform. Okay, so the blue is the real part, and if you look carefully, you'll see that the blue is kind of blue is symmetric. It kind of goes along here, and then it jumps up these two little peaks, then down, and then if it's the same, if you go from the right over here, jumps up these two little peaks and then jumps down. Whereas the orange is this is the imaginary part, and you can see here coming from the left, it sort of drops down and then a couple upward spikes. Whereas coming from the right, it goes up and then drops down for a couple. Yeah. So in fact, what happens is that the thing, The blue part is kind of purely is symmetric. It's the same reading from the left to the right as from the right to the left. And whereas the orange part is anti-symmetric, reading from the left to the right, reading from the right to the left, those are negatives of each other. That's how it works if you take the discrete Fourier transform of a signal where the values in the signal are actually real. Okay, so that's how it works. But yeah, so anyway, the main point though is that the stuff reading from the left to the right determines the stuff reading from the right to the left. So it's only really kind of useful to look at the first half of it. Yeah, and also, in fact, for most purposes, what we want is is actually the absolute values. The argument, the phase of these numbers is not so important for most of our purposes. We kind of mostly care about the absolute value of these complex numbers. And those are going to be symmetric. It's kind of the same reading from the left and the right. Okay, so so we do n is the length of this signal, then we're going to only go as far as we're going to look at the first half, because the second half is kind of more or less the same as the first half. Okay, so here's our Fourier transform. And this was for a violin, and you can see, as with most of these instruments, we've got this very big peak at the kind of the main frequency, the main frequency of the note that we're playing. It's here, and then you've got some other signals which are kind of multiples. You've got some power at multiples of the main frequency, given by these spikes that are kind of more regularly spaced that we see over here. So to display that a bit more clearly, what we're going to do is we're going to kind of rescale this. We're going to find what's the position of this main peak, and then we're going to divide the frequencies by that to display on the bottom. So how do we work out the position of this main peak? We can do argmax. So I'll call that I naught is that's the position of the absolute value, and then so so actually notice, I mean, what we were doing before we just did plt.plot, and then we plotted let's go back to how it was before. So here, notice we just we did plt.plot, and we just plotted plotted the y value. Just gave one argument specifying the y values, and that works okay. And then what's on the x-axis, you just kind of get numbers, sort of from n is the length of this array, and then on the bottom you just got 0 up to the length of the array. But now we're going to do the more usual form of plt.plot, where we specify both the x and the y. And in the x, we're going to take the just numbers from 0 up to n as before. We're going to divide by I0 being the index here around 2000 or something, where we get the maximum value. Okay, so we. Okay, so here we've got the frequencies up to so I had to just change that to make the range here going up to n over 2, because we only did the Fourier transform things up to n over 2. So we've got that numbers up to n over 2 divided by I0, so that the main frequency is here at 1, and then and then the y values are given by the absolute value of the Fourier transform. Okay. Okay, so this is a plot of Fourier transform. So let's just let's package that up into a function. Okay, so we're going to read the data file, and then we're going to convert the data to a float form data type, and then take the thing we had before. Okay, so we're going to cut down the data so that we've only got the part where there's actually something happening. Okay, so there's all those steps we did before as a function, and now let's do so here we go. Here's the thing for a flute. Flute has kind of very pure tone. It's just got almost all the power is in this primary frequency. Okay, but let's actually compare this with the plot of the data. So what we're going to do we're going to do a plot where the top half is going to just plot the data, and then the bottom half is going to plot the Fourier transform. Okay, so we're going to do and we're going to if we plot the whole of the data, then we won't be able to see very much because it'll just be too crowded. So we're just going to plot the first 1,000 points of the data, which in the top half, and then the bottom half. We're going to plot the Fourier transform, and then also let's we'll set the title here. Okay, so now top half we've got the actual plot of the data, and the bottom half we've got the plot of the Fourier transform. And here's what we get for a saxophone. And that will do for this first introduction to signal processing.